Hello, VESS scholars. For this presentation, we're going to look at Earth's contextual place in the solar system. You might think of the solar system as our exosphere because it is. And of course, NASA is best known for its exploration of that aspect of the Earth's environment, the exosphere, thinking about planetary missions like landing on the moon, for instance, or getting people to Mars or just robots to Mars. So let's look at that to begin with a little bit. So the first question we might ask ourselves is, where on Earth do we even get planets? What is even a solar system? Solar nebula theory is basically right now our model for how solar systems develop. And it's largely based on our own solar system, of course, and its characteristics. And a little bit of what we can see out in distant space using different space telescopes to understand the progression of formation of solar systems, beginning with the solar nebula, which is a cloud of gas that is spinning, and you've got that mass spinning around in a starting off, of course, as a nebulous cloud, and eventually flattening to a disk. The center part is where most of the density exists, and eventually that begins to form a protostar, and eventually fusion ignites and forms a star. Eventually, the nebula clears itself, and at that point, planets begin forming because all that nebula debris becomes planetesimals through planet formation, which is a process of condensation, accretion, bombardment, and then you have planets, essentially. And of course, that process is illustrated, and we're trying to understand that really, really well for Earth, in the formation of our natural satellite, aka the moon, right? So this is primarily thought of primarily explained as an impact hypothesis. So where this Mars-sized object slammed into Earth during the period of heavy bombardment for about 4 billion years ago, and chunks of matter were blasted off essentially as a part of that, both bodies, and then of course recoalesced in orbit around the Earth. Our natural satellite is rather large for the planet it orbits, and is moving away slightly all the time. Nevertheless, it's iconic for us, right? And we've actually had people on it. But understanding all of that and how these things work is a critical part of NASA's mission, and helps us understand our own environment. Of course, we understand our environment. Of course, that history of that solar system as best we can. We try to use models to explain it, such as, why do we have this asteroid belt? What's something called the Nice model, because it was developed in the French town of Nice by some scientists who came up with the idea. Tries to explain the positions of Jupiter, Saturn, and this asteroid belt. And during the period of the development of all of that, in the current situation, during the period of heavy bombardment, 3.8 billion years ago. But really, it goes back to the 17th century with Kepler and eventually others, Copernicus, Kepler, and Galileo, all of whom contributed to these. But Kepler's laws are really the critical piece here when we understand how things orbit stars. Or how anything orbits anything, because of course, when we launch satellites or other spacecraft, we have to think about orbits. And of course, Kepler's first law is that all planetary orbits are elliptical. There's actually no such thing as a perfectly circular orbit. We know that object that orbits that star or that object is going to be sweeping over equal areas in equal periods of time. That is, of course, Kepler's second law. And we can calculate this. And that from this, of course, it practically means that the object is moving fastest when it is nearest to the object it's orbiting, and slowest when it's further away. And then Kepler's third law governs the orbital period, or how long it takes overall, depending on the distance the object is from the something that's called the law of harmonies. Of course, it's just a mathematical equation. So as laws, they have math behind them. In our solar system, we have the inner planets, of course: Mercury, Venus, Earth, and Mars. You're all very, very familiar with those. And we have the asteroid belt at that point. And of course, the asteroid belt is not like you see in Star Wars, where all of a sudden they come out of hyperspace and there's asteroids everywhere. You come out of hyperspace in our asteroid belt, you're probably not seeing anything. It's not quite as dramatic as it sounds. Was it another planet at one point? Was it something that never became a planet? There's still a lot of debate about that. The outer planets include, of course, Jupiter, Saturn, Uranus, and Neptune. You'll notice there's one not included. That's Pluto, because Pluto is a dwarf planet. Dwarf planet. This term, actually, planet, was defined in 2006 by the International Astronomical Union, where they also created this designation called dwarf planets, which creates a category for things like Pluto, Eris, Haumea, Ceres, Makemake, and so forth, that maybe these are objects that are spherical and orbit the sun, but maybe they haven't fully cleared their orbital path. And that's that third component of a definition of a planet that's so critical. And of course, there's comets. Some of these comets come from the Kuiper belt, rather, which is like another kind of icy asteroid belt out where Pluto's kind of hanging out past Neptune's orbit. And then some of them come from something called the Oort cloud, which generally surrounds the entire solar system even further out. Those are the long period comets. Comets are just icy snowballs. Planets, of course, can only support life if they're in a place that, as far as we know, where liquid water can exist. That's, of course, because we base life on what we know here on Earth, which makes sense. That's our model for how life exists. So when we look for exoplanets in places in other solar systems, that's what we're looking for, is places where water can exist in all three states at one time. And here are some of them. These are some of the exciting ones out there, and even more have been discovered since these. You can pause it and take a look at some of these, but there's lots of information on exoplanets now. All right, what will happen to the Earth eventually? The sun will become a red giant. At that point, the Earth will become very close to the sun. Life will likely largely cease, if not completely cease, and the sun will eventually explode as a planet, become a planetary nebula, and a white dwarf. And at that point, Earth will be kind of a cold shell of what it once was. This is all going to happen, a few billion years from now, but still, nevertheless, it will happen. All right. Hope you've enjoyed this quick tour of the solar system. Let's keep walking on that VESS journey.